discussion on positive definite matrices and its application a bit more systematically. We had done this some discussion in the class, no doubt about it, but I thought a more formal presentation will be useful. And then subsequently, I'm going to follow it up with a video on um, properties and properties of positive definite matrices and Kolosky decomposition. And then from there, from Kolosky decomposition, I will lead you to LU decomposition of normal non-singular um, non-singular real matrices and cross n matrices. So let's begin today with the positive definite matrices. They are very important set of matrices with significant applications in optimization, and I'll discuss them today a bit in a bit more detail, so that you are really motivated to look at their properties very closely. And then the Kolosky computation decomposition is essentially a computational aspect of it, which we will come to later on. So we say that definition wise, we say that a real n cross n matrix could be symmetric or unsymmetric, is positive definite if x transpose Ax is greater than 0 for all x not equal to 0. So whatever be the x n-dimensional vector, x transpose Ax is always greater than 0. And a trivial example is identity matrix. X transpose Ax is going to be equal to x1 square plus x2 square plus xn square, which is strictly greater than 0 for all x not equal to 0. So this is one very simple example of a very trivial example of a positive definite matrix. And there are infinitely many positive definite matrices simply because alpha times of A is also positive definite when alpha is greater than 0, and you can create infinitely many matrices just out of identity matrix itself. Now, a matrix is said to be positive semi-definite if x transpose Ax is greater than 0, greater than or equal to 0 for all x not equal to 0. Remember, if x is 0, always x transpose Ax will be 0. So therefore, we have to always emphasize this fact that x transpose x is not equal to 0. So again, a simple true cross true example would be 1 0 0 0. And if you look at x transpose x here, that is nothing but x1 square, and this x1 square is always greater than or equal to 0 for all x1 x2 not equal to 0. But this can be 0. For example, if you take x as 0 1, then x transpose Ax is going to be 0. So positive semi-definite matrices permit this this thing that they are non-negative. This is like they are positive. Now, x transpose if x transpose Ax is strictly less than 0 for all x not equal to 0, we call it that it is negative definite matrix. Conversely, all we are saying is A is negative definite, means minus A is positive definite, because the moment you say minus of this will become greater than 0. So x transpose minus of x is greater than 0 for all x not equal to 0. So minus of A is positive definite. So no separate study is required for negative definite or negative Similarly, semi-definite matrices. And negative semi-definite matrices will be X transpose AX less than or equal to 0 for all X not equal to 0. So for example, identity matrix is a positive definite matrix and minus of identity is a negative definite matrix. This is a positive semi-definite matrix and minus of this is negative semi-definite matrix. Finally, a matrix is indefinite when for some, say, vector P1, P1 transpose A P1 is greater than 0, and for some another vector P2, P transpose A P2 is less than 0, where P1 is a vector in Rn, P2 is a vector in Rn. For example, take A to be 1 and minus 1. So X transpose AX is going to be equal to x1 square minus x2 square. So if you take P to be equal to P1 to be equal to 1, 0, then P1 transpose AX1 is going to be equal to 1. And if you take P to be equal to P2 to another vector to be 0, 1, then P2 transpose AP2 will be minus 1, which is less than 0. So this covers entire range of your matrices: positive definite, positive semi-definite, negative definite, negative semi-definite. If none of above, then it is called a indefinite matrix. Such a matrix is called a indefinite matrix. Now, if a matrix is positive semi-definite, then I have a more interesting characterization for it. Now, here onwards, I am only going to restrict my study to the study of positive definite matrices. So, I say that A is positive definite if and only if A plus A transpose by 2, which is a symmetric matrix, average symmetric matrix in some sense, is also positive definite. So this what the importance of this proposition is that it means that basically symmetric matrices have nicer properties, nicer properties than unsymmetric matrices. Like for example, their eigenvalues are always real, their eigenvectors are always real, and all that can be used to our advantage when studying positive definite matrices. So let's say that let's start with A is positive definite. This means that X transpose alpha, which is equal to X transpose AX, will be greater than 0 for all X not equal to 0. Therefore, if I take transpose, because alpha is a scalar, it also means X transpose A transpose X is greater than 0 for all X not equal to 0. Now I add and take average, so I get alpha is also equal to X transpose A plus A transpose by 2 times of X, but alpha is greater than 0 for all X not equal to 0. So the conclusion is A plus A plus A transpose by 2 is positive definite. Conversely, I'm sorry about this disturbance in the noise which has started from some adjacent flat. Let's hope the noise cancellation is working properly. Conversely, uh, if X transpose A plus A transpose by 2 times of X is greater than 0 for all X not equal to 0, then again call X transpose AX as alpha because it is a scalar. So this is also equal to alpha. So therefore, the above term here, this term here is going to be equal to X is going to be equal to 2 alpha, sorry, is going to be alpha plus alpha by 2, that is only alpha, and it says that alpha is greater than or equal to 0, but alpha is already equated to X transpose AX, which means that X transpose AX is greater than 0 for all X not equal to 0, that is A is positive definite. So mostly I hear on